This is the last section in chapter 10. And we're going to wrap up our discussion of polar coordinates. And the last thing we're going to do is we're going to see how that we can use polar coordinates to find the area of regions that we could not find the area of before necessarily, okay? Or at least not in a way that would have been simple or easy to understand, okay? And we'll also talk about arc length and polar coordinates. Remember, we talked about how we can find the arc length of a parametrized curve by using that formula. Remember, it was like square root of dx dt squared plus dy dt squared dt, where t, the parameter travels between its beginning and ending points. Now, that was just an application of the Pythagorean theorem. Yeah, that formula, that's where that formula comes from. And what we will see is we will see that when we actually use polar coordinates as our parametrization, and by the way, it is all polar coordinates are is just a special kind of parametrization, yeah? We did parametrization in general at the beginning of chapter 10, and now we've really been focusing on this particular way to parametrize things, namely with polar coordinates, where theta is the parameter, and r, the radius, depends on theta, yes? But we're going to see what the formula actually transforms into if we happen to be working in polar coordinates, because we use polar coordinates so often that it's worth our while to think that through. So we'll look at arc length again in this context, and we'll also look at surface area. Okay, so it should be fun. Okay, so let's do that. Okay, so first of all, suppose I want to find the area of this region right here, okay? So let me kind of say this right here. So this angle right here, alpha, is kind of the start of this region. Okay, so this is alpha. Right, alpha was, I just covered it up, and this is where this region stops, is right here with this angle that I've called beta, all right? And I want you to think of alpha as being theta, theta sub 0. And what I'm going to do is kind of break this thing up into a bunch of chunks, and we're going to try to come up with a formula for how to find the area of this thing, just using basic reasoning about geometry. You know what I mean? We're just going to think about geometry, okay? Okay. Now suppose I'm like concentrating on this specific one right here. I don't know. Let's just look at this guy right here. This little pie-shaped thing that happens to be sitting between theta 1 and theta 2. Does that make sense? Right here, yeah? What's a way that I could at least approximate the area of this thing, okay? Well, actually, I think there's a way that we could just straight up figure out what the area of that thing is, because this is really just part of a larger circle. Let me kind of draw the circle that I'm thinking of, okay? Kind of just, right, if I were to complete this circle, go like this, and that's a horrible circle. I got sort of squished on the bottom right there, yeah? Okay, but that's kind of the circle I'm thinking of. What is the radius of this circle? And I'm intentionally kind of highlighting this thing right here. The radius of this circle is given by that, yes? And in this curve, the curve that's going along here, the radius is given by f of whatever angle you happen to be at, okay? So again, let me just try to correct myself or redeem myself a little bit here. Okay, so it's that circle. What is that radius? What is that radius going to be given by? It's not theta 2, by the way. It's going to be the radius at that angle, yes? So what is that going to be given by? What is that radius? Can you guys help me out here? well, yeah, whatever R is at theta. So F of, okay, yeah. It's going to be F of what, Michael? F of theta 2, basically. Yeah? That's what that radius is. So what about this green area? The green area, right? So this green area right here, that thing is going to be given by, the area of the entire circle would have been pi times the radius squared, yes? So it would have been pi times the radius f of theta 2 squared. But we don't, if I just want that green stuff, I don't want the area of the entire circle, seriously, yeah? So I want to take the fraction of area that we have here. What fraction of area do we have though? Well, yeah. Yeah, theta 2 minus theta 1 is basically this tiny angle right here. That is exactly right. Theta 2 minus theta 1 is that little angle that makes up that region, yes? And I want to take that fraction of what? What are you thinking here, Michael? That fraction of the entire thing, which is, right, 2 pi would move us all the way around, correct? So what happens here? What happens to the pi's? Yeah, the pi's just cancel. And what I'm left with is, I'm going to kind of write this down here. Well, actually, no, I'll write it over here on the left, okay? So what we get is basically 1/2 f of theta 2 times theta 2 minus theta 1. See what I'm saying? Yeah? That's what the area of that little green region is right there. Yes? Oh, yes. F of theta squared. Yes, thank you. That's very important because of that 2 right there. Yeah? Okay? So 1/2 that thing squared times theta 2 minus theta 1. And in general, was there anything special about theta 2 and theta 1? No. I could have done that with any of these, yes? So in general, the ith sector, okay, all right, so first, second, like the first one would be from theta 0 to theta 1. The second one would be from theta 1 to theta 2, yes? The ith one would be from theta I minus 1 to theta I, yeah? And what it would be, it would just be the same sort of thing. 1/2 f of theta I squared times theta I minus 1, yeah? And therefore, what's the total area going to be? What would I have to do with all of these things? Well, I would add them up, yeah? So it'd be like sum I going from where to where? From 1 to n, and it would be 1/2 f of theta I squared theta I minus theta I minus 1. Now, this is going to be an approximation for the area, correct? So, but what would I do to like make this precise? Right, and I would let the difference between those two, between consecutive angles go to 0. Does that make sense? So like what would this become? This theta I minus theta I minus 1, that would get, this is almost like a delta theta I. Does that make sense? And that would get smaller, and then our approximation would become precise. That delta theta I would just call d theta. Does that make sense? So to make it precise, what would I do? Well, eventually it would just, instead of a sum, it would be the integral from where to where. Where would my angle go between to get everything? What would theta go between? Alpha and beta, yeah? And it would be 1/2 f of theta squared d, right? The delta theta I would become d what? D theta, yeah? And that's the formula that you would get when we let the thetas get closer and closer and closer to each other. Yes? That integral would become, or that sum would become an integral, and then we would get a precise formula for the area of this region. Does that kind of make sense? We just hone in on one of those pie slices, and we basically just extend that to a sum. And to make that approximation precise, it turns into an integral. And that, my friends, is what this formula is on the next page. Okay? So the area and polar coordinates formula is exactly what we just wrote down. Okay, if you have a region that's bounded by two angles, alpha and beta, yeah, both of those rays at an angle of alpha and an angle of beta kind of emanating from the origin. And then you have a curve given by polar coordinates, or given by r equal to some kind of function of theta. Then the area bounded by that polar region is given by that formula we just came up with. Basically 1/2 r squared d theta, and you just integrate from alpha to beta. Why is it that I put the restriction that the difference between alpha and beta had better not be bigger than 2 pi? Why would I put that restriction on there? Well, that just means that my angles aren't like overlapping themselves. I mean, that just makes sure that they're not too far apart or something. So the difference between the starting angle and the ending angle, there's no reason that that would ever need to be bigger than 360 degrees. Do you see what I'm saying here? Sort of get a region. Okay. Okay, any questions on that formula? I just wanted to at least give you an idea for why this formula is what it is. But any questions on that? Okay. Find the area enclosed by one loop of the four-leafed rose. And by the way, we kind of know that you guys knew that cosine of 2 theta was a four-leafed rose, didn't you? Remember, you have cosine of n theta, that's going to be a rose situation, yes? And if the number sitting next to theta is even, it doubles, like the number of petals is double that number, yeah? This is a four-leafed rose. I promise you, the sketch is going to look something like this. I mean, just think about what's going on at theta equal to 0. If I plug in theta equal to 0, which means I'm on the positive x-axis, what's my radius? If I plug in theta equal to 0, what's my radius? 1. Okay, so I'm kind of out here, right? And this is like 1 out here. And what's going to happen is the following. Let me just kind of draw some kind of breaking points here. Okay, this is like at pi over 4. This is at 3 pi over 4, like this. This rose is going to trace out the top petal like this. You're going to be at 0. You're going to kind of trace it out in this direction. It's going to be at 0. And then I'm telling you, then the radius is going to become negative once I get beyond pi over 4. Think about it. What's the cosine of 2 times pi over 4? That's the same thing as the cosine of pi over 2. What's the cosine of pi over 2? 0, yeah? And then suddenly, once I get between pi over 2 and pi over 4, right, so let me just kind of specifically say when this happens. This is for 0. Oh man, I just stinking erase that whole thing. Okay, so this is going in this direction. Okay, so 0 less than or equal to theta less than or equal to pi over 4. You sketch out this part of it. Then what happens when you're between pi over 4 and pi over 2? Cosine of twice that is going to be negative. So when I'm in this part right over here, right, when I'm in this region, the radius is actually negative, which means I flip down into the opposite quadrant. Does that make sense? I would have been in quadrant 1, but now I flip across to quadrant 3, yeah? So the next part of it is going to go like this. It's going to kind of grow outward to a distance of 1, okay, like this, okay? And that happens between pi over 4 and pi over 2. So this is for pi over 4 equal to or less than theta equal to or less than pi over 2, okay? Similarly, if I'm between pi over 2 and 3 pi over 4, the cosine of twice that is still negative, so I would flip across into quadrant 4, yeah? And this thing's going to go like, I don't know, let me see, I'll use yellow this time. This thing is going to shrink down like this, okay? Okay, so this is going to be from pi over 2 equal to or less than theta equal to or less than 3 pi over 4. I sketch out that portion of the curve, okay? And do you see what the pattern is going to be here a little bit? So, I mean, now I'm back to the origin again. And I'm telling you the next place that we go is here. I'll draw this one in black. The next place that we go is right here. Okay. Actually, once I get beyond 3 pi over 4 down to pi, the cosine of twice that is going to be positive again. So I'm back up there. So this thing goes like this. Okay, so I mean, just to mark where we've gone, it was 1, 2, 3, 4. Okay, so this is the fourth chunk of this thing. You see what I'm saying? Okay, now I'm just going to continue drawing this thing. It's going to go back like this. Here's the fifth part of this. The sixth part is going to be like this. Okay, here's the sixth part, and then the seventh part. And then finally, I finish this thing right here, the eighth part. You can kind of think about why that happens to be the case, but there is our 4-leafed rose right there, yes? It kind of goes whoop, whoop, and it kind of whips around in interesting parts of the rose as this thing is being sketched out, okay? Hopefully that kind of makes sense, okay? We're gonna look at some examples in Desmos here at the end, but I just wanted to at least sketch that one out. But this is asking for the area enclosed by one loop of the 4-leafed rose. One loop, okay? What my suggestion is that we actually find the area in half of this, okay? Like half of one of those loops, okay? So what's the angles that give us just half of that thing? Yeah, 0 to pi over 4. Do you see what I'm saying? It's going to be 0 to pi over 4. Okay, and look, so that area, okay, so let me just say area of one loop is equal to, I'm going to have to double this. It's going to be 2 times 1/2 times the integral from where to where? What's the integral? Or what are the bounds for the angle? 0 to 45 degrees. And then you do r squared, correct? It was f of theta squared. So it's going to be cosine squared of 2 theta d theta. Okay? So of course, this 2 and this 1/2 just cancel. And we end up with the integral from 0 to pi over 4 cosine squared of 2 theta d theta. Okay. What do I do? How do I integrate this? You guys thought that you could forget everything from chapter 8, right? How am I going to integrate this thing? Yeah, one of the power reducing formulas. Yeah. Remember when we were doing trigonometric integrals? Yeah. Trig integrals. What did I do? Okay. What did I do in the case where I had like an even power of cosine? You used the half angle formula. Yeah. I think that's what you were saying, right? Right, Jared? Half angle formula says this is 1/2. I remember that thing had a 1/2 in it. 1/2, and what was it, Jared? 1 plus cosine of 4 theta, because it would be twice whatever the angle is, yeah? This thing is half the angle of the formula side of this thing, okay, d theta. Now, I want to point something out to you, that what I'm about to tell you is one of the most practical tips I can give you. Think about this guy. Think about the cosine of 4 theta. when I integrate that, what am I going to get? Think about it. So cosine of 4 theta, when I integrate that, I'm going to get, what's the antiderivative of cosine 4 theta? 1/4 sine 4 theta. 1/4 sine 4 theta. And of course, this guy is going to be evaluated between 0 and pi over 4. But for crying out loud, guys, when I take 4 times pi over 4, that's pi. What's the sign of pi? 0. What's the sign of 0? 0. So what does that part integrate to? 0. Okay? So in the end, interestingly, this is just 1/2 the integral from 0 to pi over 4 of just 1 d theta. That cosine part just integrates to nothing. And that happens a lot with these problems, okay? You end up having some remnant cosine thing that actually doesn't end up contributing anything. And so you kind of do what I just did. You sort of say, okay, that thing is not going to contribute anything, and you cast it aside and just deal with the simple stuff that's left. Now, if I integrate the constant 1 from 0 to pi over 4, isn't that just the length of the interval? Yeah? It's just going to be the difference between the endpoints. And the length of that interval is just pi over 4, correct? So what are we going to end up getting as the answer? Pi over 4 times 1/2, which is pi over 8. Exactly right. Okay, pi over 8. So the area in one of those leaves happens to be pi over 8. Okay? Make sense? Hopefully that kind of makes sense. Any questions on that? Questions? Any questions? Sketching, by the way, I would really encourage you, sketching these, oh man, I just erased what I was going to do here. Sketching these roses is kind of fun. You can kind of see the thing move around. It moves around in this really interesting kind of serpentine way as you're sketching the thing out. It doesn't necessarily go this loop, and then this one up here, and then this one up here, and then this one down here. It kind of goes and it stays really smooth. There's no real sharp points at all, and it just moves in this real nice serpentine way. Okay, this was the first part right here, and then the second part was here, and then the third part, and then the fourth part, and then the fifth part. This is kind of cool, right? I think it's kind of interesting to think about that. The 8th part is right there. Okay, cool. All right, let's talk about some other stuff here. Find the area of the region that lies inside, you guys know that that's a circle, right? 3 sine of theta. Remember we did 6 sine of theta before? And that was a circle of diameter 6 sitting on the origin. Remember that? So what's this circle r equal to 3 sine theta? That's going to be a circle of diameter 3 sitting right on the origin. Yeah? Okay. And outside that cardioid, r equal to 1 sine of theta. You guys know what that looks like, don't you? The cardioid looks like this. We were kind of messing with that yesterday, weren't we? Yeah, remember that? And then the circle of radius 3, well, how high is this right here? How high is this point where the point of the heart is? Think about it. That would be at pi over 2. Theta equal to pi over 2, so it'd be 1 plus sine of pi over 2, which is, I think I heard Jared just say it. Sine of pi over 2 is 1, which the 1 plus 1 is 2, yeah? But I said that this is a circle of diameter 3, yeah? That sits on the origin. So this thing is going to go a little bit of, oh man, what am I doing with my circles today, okay? So this is supposed to be 3. So basically what they're asking us for here is the area between, like in this little crescent moon-shaped thing. Does that make sense? It says outside of the cardioid, but inside the circle. Yeah, outside the cardioid, but inside the circle. In order to do that, we're gonna have to figure out like what our starting and ending angles are. Okay, what this alpha is and this beta is. you know, where we kind of start the region and end the region. Does that make sense? Okay. So what is that area going to be? Okay, so what's the formula for that area going to be? I mean, I don't know what those angles are yet, but we could at least write down a formula, couldn't we? So it's going to be the outside kind of circular region, yes, minus the inside cardioid region, correct? So isn't that going to be 1/2 integral from alpha to beta? What's the outside? Like what is the, okay, so it would be r squared, correct? The outside thing is the circle. So it would be 3 sine theta squared d theta. And then I would have to subtract the area inside the cardioid between those two angles, yes? So it'd be minus 1/2 integral from alpha to beta of what? R squared again, yeah? So r squared, r in this case is 1 plus sine of theta. That thing would be squared d theta. Do you see what I'm saying here? Yeah? Right, written another way, you could just write this as 1/2. You could write it as one huge integral. Integral from alpha to beta. And what would it be? Like 3 sine, or actually not 3. What would it be? If I squared this thing out, it wouldn't be 3 anymore. What would it be? It would be 9 sine squared of theta, yes? Okay, we've pulled out the 1/2. Now I'm going to multiply out this other thing. It's 2, what is it? 2 or 1 plus 2 sine theta plus sine squared theta. So it's going to be, or actually there's going to be a minus sign here, sorry. When I multiply this out, it's going to be minus 1 minus 2 sine of theta minus sine squared theta d theta. Okay? So in the end, what does the integral end up being? 1/2 integral from alpha to beta, 9 sine squareds minus the sine squared. By the way, it's negative because of this minus sign, right? That minus sign negated that whole thing when I multiplied it out. Okay? So 1/2, what's 9 theta squared, or 9 sine squared theta minus sine squared theta is how many sine squared theta? 8. So it's going to be 8 sine squared thetas minus 2 sine of thetas minus 1 d theta. And would you guys know how to do the antiderivative of each one of those things? Do you know the antiderivative of sine theta? Yes. Do you know the antiderivative of 1? I hope you do. What about sine squared? How would you deal with sine squared? Half angle formula again. So what's the only question we have? So the whole point is we know how to deal with these things as antiderivatives, but what's the only question that remains? Just what in the world are the angles? Yeah, what are these things? What is this and what is that? Okay, we want to know what those angles are. Let's not spend any time like doing the integral necessarily, because that's going to be the easy part. The only thing that really remains is we need to figure out what those angles are. What are those bounds? That's the only hard part that really remains. Does that make sense? So I'm not going to actually do the integral, but I'm going to concentrate on trying to find those angles right now. But any questions on what we just did? Yeah, Kira. Sine to the, say again? No, it just says to the second power. That's just a S, that's the dot on the I. Does that make sense? And this is a dot on the I, and this is a dot on the I. Yeah, thank you. Okay, so does this make sense, what we did? Area of the outside thing minus the area of the inside thing, yes? So the only thing we're gonna do now is what? Find the angles. Doing the integral is easy. We just need to know what the bounds are, yeah? Okay. All right. I'm going to erase this and I'm going to go over into Desmos. Okay. Are you guys ready? Okay. So let's go do this thing. Here we are. I've kind of graphed these things right here. Do you see it? Okay, so there's the cardioid and there's the circle. And again, we want to know what these angles are right here. Like what's this angle and what's this angle right here? That's the goal. We want to know what those angles are, yes? Okay. And of course, here are the formulas, r equal to 3 sine theta and r equal to 1 plus sine theta, yeah? Basically, what we want to do is figure out where those two curves intersect each other, don't we? At what angles do those two curves intersect? Okay. So what would I do to figure out where those two curves intersect? What do you think I would do? Yeah, the radii would have to be the same, and they would have to be the same at the same value of theta. Does that make sense? The radii would have to be the same at the same value of theta. So if the curves literally cross those points at the same moment, right? Because you have to remember we have a parameter that's moving us along these curves. Watch this. I'll actually animate this. You guys ready? Watch. Okay. So do you see those dots on those curves? Okay. What's kind of interesting is, do you see that circle gets traversed like a little bit quicker? Remember, it went around the circle twice in 2 pi. And the cardioid is getting traversed a little bit more slowly. Do you see that? Okay. So that's interesting, right? So we want to figure out when it is that those two things cross each other and actually hit each other exactly on the curve, yeah? So the way that we're going to do that, let me pause this. That's cool, but you know. So, I mean, basically, let's see here. When is this happening? So it looks like it's happening like right here, yes? And then it's happening again right here. Do you see that? So it's happening right here and right here. Here and here, yeah? So someone said, hey, just set the two things equal to each other because the R's would have to be the same at the same theta, yeah? So let's do that. We would go 3 sine of theta would have to be equal to what? 1 plus sine of theta. Yes? So what's that mean? Right, like if I move this over here, I have how many sine thetas left? 2 sine theta is equal to 1. So what's sine of theta? Sine of theta is 1/2. And there are 2 times where that happens, which works out perfect for us because we were after 2 angles. Yeah? When does that happen? Theta equal to, I know I've been pushing you guys on this lately. That's the thing about polar coordinates. Like if there were some gaps in the trigonometric foundation, it starts to be brought to bear here. So what angle's theta? There's pi over 6 and pi over 6 and 5 pi over 6. Exactly right. So our alpha would be the first guy. Okay, so this would be alpha, and our beta would be the second guy. Yeah? So that's where we would integrate between those two things. Now, does that make sense? Hopefully. Now here's something kind of interesting, y'all. There's another place where these curves intersect. You see it? I mean, it's kind of an obvious place. There's another place where these curves intersect. 0, 0. Why didn't we find that? Because what we did is we said, well, we got to find the places where the curves intersect. We did what kind of felt natural to us, kind of find the places where they intersected. But why didn't theta equal to 0? Why didn't theta equal to 0? Why didn't theta equal to 0 kind of come up? Well, let's kind of check this out in slow-mo again. When I'm at t equal to 0, are those curves intersecting? No, because on the blue curve, I'm away from the origin. Does that make sense? So let's watch what happens as I move this along. Okay, they intersect right there. The blue thing goes, they intersect again right there. The red guy goes and hits the origin, yes? But is the blue guy there at the same time? No. So then this guy takes off to go around the circle again, the red guy, and the blue guy comes and then decides to visit the origin, yes? So the issue is they didn't hit the curve at the same value of the parameter, yeah? They were never at the origin at the same value of the parameter, and then the red guy comes back to the origin now. And guess what? The blue guy's back over there. So you see they were never at the origin at the same value of the parameter, yes? That is why we missed the point 0, 0. You have to be on the lookout for that because sometimes you actually want those points for various reasons, but we didn't really care about it here. They did actually intersect each other at the perfect value of the parameters when it came to finding this area. But do you see why we missed the point 0, 0, or we missed the origin, yes? It's because the things were kind of out of sync when that happened. You were at different points on those curves when that happened, okay? Any questions on that? I think that's kind of a cool thing to think through, but any questions? Okay, you can sit there and just watch that thing run for a while. It's sort of a cool thing, right? But yeah, that. Okay, back in here, back into the slideshow. Let's continue. All right. Again, we already talked about this. Why didn't we find 0, 0 as an intersection point, even though it was? Well, because the parameter, like where we were on each one of those curves, were at different places. Like it visited 0, 0 at a different time than for the one curve than it did for the other. Yeah. So that's the essence of what was happening. Okay. Arc length. Let's talk about arc length. And actually, rather than actually go and go through all of this, or actually do an example, what I'm going to do is I want to show you why this happens to be true. Okay, what is x equal to in the polar coordinates, and what's y equal to? What's x equal to and what's y equal to? Yeah, r cosine theta, and y is r sine of theta. And of course, you know that r is like some kind of function of theta. Does that make sense? Yeah? Okay. And you know that the formula we had before was like integral from first value of the parameter to second value of the parameter, dx dt squared plus dy dt squared, correct? Well, what is dx d theta? What's dx d theta? We kind of did this yesterday, and remember, r is actually a function of theta. So what would I have to use when I compute dx d theta? What kind of a thing is this? Starts with a P. It's a product, yeah? I would use the product rule, right? So I would go the first, I don't know, let's go first times the derivative of the second, which is negative sine of theta, plus the derivative of the first, I'll call that dr d theta, times the second, which is cosine of theta. Okay? Does that make sense? That's what dx d theta is. Yeah? What's dy d theta? Okay, dy d theta is, we did this yesterday, but I think it's good to just redo this. It's going to be r times, so it's the first times the derivative of the second, r times cosine theta, plus the derivative of the first, dr d theta, times the second, which is sine of theta. Okay, but the formula for arc length told us to take these derivatives and do what to them? The formula for arc length that we had before said to take these derivatives and do what? Square them and add them together, yeah? Okay, so look, I'm gonna, oh man, what did I just do? Somebody help me out here. What was dx d theta? Was that minus r? That was minus r sine of theta plus dr d theta cosine of theta, right? And what was dy d theta? R cosine of theta plus dr d theta sine theta. Okay, what if I square those things? Okay, let's kind of think about this. Dx d theta squared plus dy d theta squared, okay? What if I square those things? What am I going to get? Well, if I square dx d theta, I'm going to get r squared sine squared theta, yes? And then I'm going to have the two things multiplied together, but that's going to happen twice, yes? Kind of the inner and outer terms, the cross terms. I'm going to have r sine theta, dr d theta, cos theta. That's going to happen twice, okay? So it's going to be minus 2r dr d theta sine theta cos theta. Okay? And then I'm going to have the square of the last thing, plus dr d theta squared cosine squared of theta. That is all coming from, that's all coming from dx d theta and squaring it, okay? All of that comes from squaring dx d theta. What about the other stuff? It's going to be plus r squared cosine squared theta. And instead of a minus 2r dr d theta sine theta cos theta, what am I going to have? Plus 2r dr d theta sine theta cos theta. Okay? And then it's going to be plus dr d theta squared sine squared theta. Interesting. What happens to the middle terms? They absolutely cancel. That's amazing. So all this stuff right here is dy d theta, what we get when we take dy d theta and we square it. Yeah? But this guy here cancels this guy here. What's this junk going to reduce to? Think about it. R squared plus r squared sine squared theta plus r squared cos squared theta. What's that going to be? R squared. What about this junk right here? What's that going to reduce to? Don't I have the same thing attached to sine squared and cos squared? Yeah. So what's that going to reduce to? Dr d theta what? Squared. Right? So weirdly, dx d theta squared plus dy d theta squared simplifies to just r squared plus dr d theta squared. Yeah? Daniel.
So why did the sine and cosine cancel the r squared? Like why do those two terms cancel?
They don't cancel. R squared sine squared plus r squared cosine squared. If you factor out r squared, what's sine squared plus cosine squared? Yeah. R squared sine squared plus r squared cos squared, that's just r squared. Yeah? Same thing with the other thing. Yeah? Except the constant term is dr d theta squared. Make sense? So here, I'm going to erase this. That's why the formula is this. Do you know what I'm saying? That is why the formula is this. Do you guys realize this right here is r squared? Yeah? And what's this thing? dr d theta squared. That's what's sitting underneath that square root right there. So once all of that junk canceled, all we were left with was that. So this really is just an extension of what we had before. Dx d theta squared plus dy d theta squared. That thing looked really complicated, but then some nice simplification and cancellation happened. Yeah? So we'll come back next time. We'll look at some examples for this, and we'll also look at surface area.